So Algebra Lecture 20, and today I'm going to talk about group isomorphisms. So we'll start with a bit of review. We have a function f from a group G to group G prime is a homomorphism if writing the group operations as multiplication, f of x, y is f of x times f of y for all x and y in the group. And associated with f, we have the kernel of G, which is all x in G, such that f of x is the identity in G prime. And the image of G, which is all y in G prime, such that y is equal to f of x for some x in G. So we can draw a picture of this. We have G and G prime and a function f from G to G prime. We have the identity in each group. Call this one E prime. And we prove that for homomorphism, f of E is always E prime. So the identity always gets mapped to E prime, which means E is always in the kernel of F. But the kernel of F can be bigger. There can be a larger set of elements. Call this K. These are all the elements that get mapped to E prime. Meanwhile, any other element X, if it's not in the kernel, it still gets mapped to some element f of x over in G prime. And sitting in G prime, we have the image of G. I'll just write this as f of G for short, f of G. This is all the elements in G prime, which come from some element in G with this map F. Okay. Okay. Any questions about that? And there's some nice properties of homomorphisms and subgroups. So let me just collect some of them here. First of all, the kernel of F is a normal subgroup of G. And the image of F is not necessarily a normal subgroup, but it is a subgroup of G prime. And the proofs are straightforward, and I proved the kernel is a normal subgroup once or twice last week. If X and Y are in the kernel of F, then f of x inverse y is f of x inverse f of y. Each of these is the identity, and this is the identity. So the kernel is closed under multiplication and taking inverses. So the kernel of F is a subgroup. And if X is in the kernel and Y is in the group, then f of yx y inverse is f of y, f of x inverse, f of y inverse, but X is in the kernel, so f of x inverse is the identity. So this is f of y inverse, which is again the identity. So the conjugate of an element x in the kernel by any element y is the identity. So K is a normal subgroup. So this is a basic argument in group theory, which is certainly in the notes and you've seen now a couple of times. Y is the image of subgroup. So suppose we let y and y prime be in the image of G, right? Again, f is this function from G to G prime. So in the image of G means there exists x and x prime in G such that y is f of x and y prime is f of x prime. But it follows that y times y prime is f of x times f of x prime, which is f of xx prime. Xx prime is in G because G is a group. It's closed under multiplication. So y prime is in the image of f. And y inverse, which is f of x inverse, but that's the same as f of x inverse. So this is also in the image of f. So the image of f is a subgroup of G prime. It's closed under multiplication and taking inverses. So that f from G to G prime be a homomorphism of groups, with kernel K. So K is normal subgroup. So we have a quotient group, G mod K, which is all of the left cosets of the subgroup K. If we have xk and yk, these are two left cosets. If they're equal, what does that mean? This is the case. That means that x inverse yk equals k, which means x inverse y is in the kernel, which means f of x inverse y is the identity. But this is f of x inverse times f of y. So if I multiply by f of x, I get f of y. So if the left coset xk equals the left coset yk, f of x equals f of y. So we can now define a function, I'll call it f tilde, from G mod k into G prime. So this is a function on cosets. F tilde of xk is equal to f of x. And if we choose a different representative of this coset, we still get the same value in G prime. And this function, f tilde, is also a group homomorphism. We've constructed a new homomorphism. So let me just write this. I'll claim f tilde from G mod k into G prime is a homomorphism. And the proof of the claim is as follows. Suppose I take f tilde of the coset xk times the coset yk. Well, the product of these two cosets is xyk. The definition of f tilde is this is f of xy. But f is a homomorphism. So this is f of x times f of y. But f of x is f tilde of xk, and f of y is f tilde of yk. So f tilde is a homomorphism. We also have the canonical homomorphism, pi from G to the quotient group, defined by pi of x is the coset xk. So we actually have, if you like, two paths from G to G prime. We have the function f, which is a homomorphism from G to G prime. But I also have associated with f, k, which is a normal subgroup, the kernel of f. And from G to G mod k, I have this canonical homomorphism pi. And from G mod k to G prime, I have this new homomorphism I just constructed, f tilde. So if you stake an element x in G, you can go to G prime directly under f, or you can go take this path through G mod k. And I claim no matter which path you take, you always end up in the same place. Because if you go this way, we're looking at the composite function f tilde composed with pi applied to x. That's a composite function, just like in Calc 1. This is f tilde of pi of x. But pi of x is the coset xk, and f tilde of that coset is f of x. So for all x in the group, f tilde composed with pi is equal to f. Moreover, f tilde from G mod k to G prime, it's not just a homomorphism, it's an isomorphism. That means it's one-to-one and onto. So why is it onto? That's easy to see. For all x prime in G prime, or let's say, sorry. I don't want to say that, that's not true. It's not an isomorphism, but it is one-to-one. And how do we prove that? If f tilde of xk equals f tilde of yk, if you have two cosets that get mapped to the same point, then f tilde of xk is f of x, f tilde of yk is f of y, so f of x equals f of y. So if I multiply by f of x inverse, the identity is f of x inverse times f of y, which is f of x inverse y, which means x inverse y is in the kernel, which means exactly that xk equals yk. So if two cosets get mapped to the same element of G prime by this function f tilde, xk equals yk, this function is one-to-one. So this induced map is always a one-to-one function. Let's look at another example of a homomorphism. So suppose I take the group GL2R. This is the set of all matrices A, B, C, D, 2 by 2 matrices with A, B, C, and D real numbers, and AD minus BC different from 0. So we can define the determinant. This is the definition. Of a 2 by 2 matrix as the number AD minus BC. So GL2R, this is all matrices A, B, C, D, where the determinant, call this capital A, the determinant of A is not 0. And I claim GL2R is a multiplicative group, and this function, the determinant, which sends a matrix to a number, is a homomorphism. So we've seen this before, but let me just jot down the proof again. Suppose I take A to be the matrix A, B, C, D, and B to be the matrix E, F, G, H. So in that case, the product AB, if I do my matrix multiplication, is AE plus BG, AF plus BH, CE plus DG, CF plus DH. And the determinant of the product AB is this number times this number minus this number times this number. So this is just high school algebra. If you multiply these things through, you get ACEF plus ADEH plus BCFG plus BDGH minus this ACEF plus ADFG plus BCEH plus BDGH. I have an ACEF that cancel. I have BDGH that cancel. So I'm left with this and this. So I have ADEH minus ADFG plus BEFG minus BE what is this? Minus BECH. So I have, if I factor out the AD from this, I have AD EH minus FG plus BE I factor that out, I have FG minus CH, BE, FG, oops, this is a C. Factor out BC, I have FG minus EH. This is the negative of this. So this is AD minus BC, EH minus FG. Lo and behold, this is exactly the determinant of A times the determinant of B. So this determinant is multiplicative, right? I mean, this is a calculation that you need to do on a piece of paper really several times. Make sure that it all makes sense, and just getting used to doing this kind of algebra. But a corollary of this immediately is that the group of matrices with non-zero determinant is closed under multiplication. So if the determinant of A is not zero, and the determinant of B is not zero, then the determinant of AB, which is determinant of A times determinant of B, it's a product of two non-zero numbers, is non-zero. So therefore, if A and B are in GL2R, this group, then the product AB is in GL2R. So GL2R is closed under matrix multiplication. You can also observe that if I is the identity matrix, the determinant of I is 1 times 1 minus 0 times 0 is 1, which is not 0. So this GL2R certainly contains the identity. And every matrix has an inverse. Every matrix with non-zero determinant. A inverse is, I claim, the following. So if A is A, B, C, D, this is going to be D over the determinant. Let me just write delta to be AD minus BC. D over delta, A over delta, minus B over delta, minus C over delta. So this is a matrix. The determinant delta is non-zero, so I can divide by it. What is the determinant of A inverse? It's D over delta, A over delta, minus B over delta, minus C over delta. That's AD over delta squared. Minus times minus times minus is minus BC over delta squared. That's AD minus BC over delta squared. AD minus BC, that was just the determinant delta. Delta over delta squared. So this is 1 over delta, which is not 0. So this is non-zero determinant. And if I multiply A times A inverse, A, B, C, D, D over delta minus B over delta, minus C over delta, A over delta, I get AD minus BC over delta, minus AB plus AB over delta, CD minus CD over delta, and minus BC plus AD minus BC over delta. This is just 1, 0, 0, 1. This is the identity. So a matrix A with a non-zero determinant has an inverse. So that's the proof that GL2 is a group. And we've also at the same time proved that this determinant function, which takes a matrix with non-zero determinant and moves it to the non-zero real numbers. That is the non-zero, positive or negative. These are the non-zero reals, which is a multiplicative group, right? You can multiply and divide multiplicative group. And this is a homomorphism. Because the determinant of the product is the product of the determinants. And what is the kernel of the determinant map? This is all matrices A, B, C, D, A equal A, B, C, D, such that determinant of A is the identity. What's the identity for the multiplicative group of the reals? It's just the number 1. So this is all matrices with determinant 1, which is the group I called SL2R. GL2R is 2 by 2 matrices with non-zero determinant. SL2R is 2 by 2 matrices with determinant 1. So SL2R is a normal subgroup of GL2R. So there's a map from GL2R, the quotient group, into the non-zero reals. Call it determinant twiddle. In fact, if X is any number, or say T is any number different from 0, and A is the matrix T0, 0, 1, then the determinant of A is T times 1 minus 0 times 0, that's T. So this map is onto. Every non-zero real number is the determinant of some matrix. Here's a trivial example. So this map, and we know this is 1-to-1, so if it's 1-to-1 and onto, this is an isomorphism. So this quotient group, GL2R mod SL2R, it's a multiplicative group which is isomorphic to the non-zero reals. That's kind of interesting. So now we're really doing group theory, and this is, so what I've just done is review some things that I had done last week and give maybe one more example of an interesting group. Any questions about this? So there are several results that are central to group theory, which are isomorphism theorems. So we can say that groups G and G prime are isomorphic if there exists a homomorphism F from G to G prime that is 1-to-1 and onto. if F from G to G prime is an isomorphism, then it has a unique inverse function, F inverse from G prime back to G, which is a homomorphism, such that, so sort of here's our picture. Here's G and here's G prime. I have F going from G to G prime and F inverse from G prime back to G. So if I compose them, F inverse composed with F, this is the identity function on G. And if I start at F inverse and compose with F, this is the identity function on G prime. And an equivalent statement is that F from G to G prime is an isomorphism if and only if there is a homomorphism, I'll call it F inverse from G prime to G, such that F inverse F is the identity on G, and F composed with F inverse is the identity on G prime. Okay. Any questions about any of this? Okay, so I want to prove what is called the first isomorphism theorem. So we start with a function f from G to G prime, which is a group homomorphism, that K be the kernel of F, and let H be a normal subgroup of G such that H is contained in K, which is of course contained in G. So H and K are both normal subgroups of G, and K is the kernel of the homomorphism. Now, because H is normal, G mod H is a group, it's the quotient group. And from G to G mod H, there is this canonical homomorphism. So that pi is what is called the canonical homomorphism. Pi of x, the element x, is the left coset xh. That's how pi is defined. So there is a unique homomorphism f tilde from G mod H into G prime such that, well, let me draw the picture and then I'll write down the conclusion of the isomorphism theorem. We have G goes to G prime by this function f. We have the quotient group G mod H and pi from G into G mod H. And there's a unique homomorphism f tilde from G mod H into G prime such that the way we say it in mathematics is this diagram commutes. If I go f tilde composed with pi, so I take an element x, I go to the coset xh and then f tilde of xh, that's the same as going from G directly to G prime. F tilde composed with pi is the same as f, is equal to f. Moreover, if f is onto, then f tilde is onto. If f is onto and H is actually the kernel, then G mod K or G mod H, same thing in this case, is isomorphic to G prime. Whew. So I hope you're following along in the notes, because as I go from one piece of paper to another, what I've just written disappears from the screen and it's hard to remember it. All right, so I need to prove all this. So the crux is, how do you construct this homomorphism f tilde? So there's what might be called an obvious method to construct f tilde, namely f tilde of a coset xh equals f of x. So the question is whether this makes sense. This is well defined. We have to show that f tilde is well defined. What this means is that if you have a coset xh, which can also be written in the form yh, then we have to show that f of x equals f of y. But this follows from the fact that h is contained in the kernel of f. If xh equals yh, that's the same as saying f of x inverse y is in h, which is contained in k, the kernel, which means f of x inverse y is the identity. But if the identity is f of x inverse y, because f is a homomorphism, that's f of x inverse times f of y. If you multiply by f of x from this equation, you get f of x equals f of y. So I've just proved that this function f tilde is well defined on the quotient group. And why is this equation true? Because if I take x, it goes to the coset xh here under pi. And f tilde sends xh to f of x. And of course, f sends f to f of x. So what I just said and wrote down shows this relationship is true. Now, if f is onto, every element in G prime is of the form f of x. So every element in G prime is of the form f tilde of xh. So if f is onto, f tilde is onto. And if f is onto and h is the kernel, well, if h is the kernel, this map is 1-to-1. So f tilde is 1-to-1 and onto. So f tilde is an isomorphism. So this is the first isomorphism theorem. Let's see if we can find an example of this that I can write down. Suppose I let G be the cyclic group of order 15. So it's generated by some element A. So I can write the elements as a squared up to a to the 14th, where a to the 15th is the identity. And suppose I let G prime be the cyclic group of order 5, generated by some element B. So this is b squared, b cubed up to b to the 4th, where b to the 5th is the identity. And let's do an experiment. Suppose I define f from G to G prime by f of x equals x cubed. Is F a homomorphism? So suppose we let x equal a to the k and y equal a to the L. So then f of xy is going to be xy cubed, which is x cubed times y cubed. Maybe I'll do it better like this. F of xy, this is f of a to the k times a to the L. That's f of a to the k plus L. That's equal to a to the k plus L cubed, which is a to the 3 times k plus L, or a to the 3k times a to the 3L. Looks like it might be okay. Maybe let's just see that that f is well defined. Is f well defined? So we have that a to the m equals a to the n if and only if m and n differ by power of 15, if and only if m is congruent to n mod 15. So if a to the m equals a to the n, then 15 divides m minus n, m is congruent to n mod 15. Of course, if 15 divides m minus n, 5 certainly divides m minus n, which means b to the m equals b to the n, because b to the 5th is the identity. So f of a to the m is b to the m, which is b to the n, which is f of a to the n. So this function is well defined. And because it's well defined, f of a to the k times a to the L, that's f of a to the k plus L. That should be, oops. Yeah, I should have defined it more carefully. So I'm defining the function g from g to g prime by f of a to the k equals b to the k. That's how I want to define this function. Sorry, equals b to the 3k. Right. So let me just do this again more clearly. So G, I'll call it gamma 15. This is cyclic group of order 15. G prime, I'll call it gamma 5, is the cyclic group of order 5. And define F from G to G prime by F of a to the power k is equal to b to the power 3k. Actually, I'll just make it easier. A to the power k gets mapped to b to the power k. So we want to ask, is f well defined? So a to the m equals a to the n means that m is congruent to n mod 15, because a has order 15. But if 15 divides m minus n, so does 5. M is congruent to n mod 5, which means b to the m equals b to the n. So the answer to the question is, if well defined, yes. Because if you have two representations of the same element of G, they get mapped to the same element of G prime. And f of a to the k, a to the L, is f of a to the k plus L. That's b to the k plus L. That's b to the k, b to the L. That's f of a to the k, f of a to the L. So this is a homomorphism. Right? This is a homomorphism. What is the kernel of f? It's all elements a to the k in G, such that f of a to the k, which is b to the k, equals the identity, which is all a to the k in G, such that when is b to the k equal to the identity? When k is divisible by 5. K is congruent to 0 mod 5. So what powers of a are the form a to the 5th? You have the identity, a to the 5th and a to the 10th. These are the powers of a divisible by 5, up between 0 and 15. 0, 5, and 10 are the multiples of 5. Between 0 and 14, or 1 and 15. So that's the kernel of f. That's my subgroup. Subgroup of G. So my group G mod K is isomorphic to G prime, where if I take this cyclic group of order 15 modulo the subgroup E a to the 5th and a to the 10th, that's isomorphic to the cyclic group of order 5. And this is an instance of the general fact that if D is a positive integer and divides n, then if I take the cyclic group of order n, divide it by the cyclic group generated by, so suppose gamma n is generated by the element A, take the cyclic group generated by the element n over D, and this is isomorphic to the cyclic group of order D. Again, to understand this takes some work. Let me prove one more basic theorem in group theory, which is called the Correspondence Theorem. And it says the following: let F from G to G prime be a surjective, which means onto, group homomorphism with kernel K. So I have group G and a subgroup K. And I can have intermediate subgroups. I can have subgroups H of G that contain K. So I'll write script L of GK. This is the set of all subgroups H of G that contain K. So all such H. Here I have G prime and my homomorphism F from G to G prime. Of course, sitting in G prime, there's always the subgroup consisting of only the identity. And let L of G prime just be all subgroups of G prime. So L of GK was all subgroups of G that contain K. L of G prime is just all subgroups of G prime. So I want to notice if H is a subgroup of G, then F of H is a subgroup of G prime. I already showed that. Yeah, I already showed that, I believe, because if you take two elements of F of H, F of X and F of Y, that's F of X, Y. So if X and Y are in H, then X times Y is in H. So the product of two elements in F of H is again an element in F of H. And F of X inverse is F of X inverse is also in F of H. So if I take the image of all elements in the subgroup H under this function F, I get some subgroup F of H contained in G prime. F maps G onto G prime. F restricted to H maps H to F of H. F restricted to the kernel maps everything to the identity. So we have a picture like this.
Sorry, Professor, do you mind just reading out that last line on like the other bottom, F of, exactly that F of X plus the F of.
So this is just showing that if H is a subgroup of G, its image F of H is a subgroup of G prime. So if F of X and F of Y are two elements in F of H, then if I multiply them together, F of X times F of Y, but F's a homomorphism. So that's F of X times Y. X times Y is in H because H is a subgroup enclosed under multiplication. So F of X times Y is in F of H. So F of H is closed under multiplication. And it's also closed under taking inverses, because if I take F of X and the inverse of that element, that's F of X inverse. If X is in H, so is X inverse. So this is also an F of H. So that's just what I wrote over here. It simply proves that the image of a subgroup of G is a subgroup of G prime. And I would like to show that, in fact, F maps onto every subgroup of G prime. If I take any subgroup of G prime, it's of the form F of H for some H over in G. So here I have G goes to G prime under F. I have the kernel of K, which gets mapped to the identity in G prime. And suppose I have H prime, so that H prime be any subgroup of G. So let's define F inverse of H prime. This is going to be all X in G, such that F of X is in H prime. So if a picture of that's the following. Here I have G and G prime. Here's the identity. And here I have a subgroup H prime. And I look at all X and G, where F of X gets mapped into H prime. So all of those X's, such that F of X is in H prime, I'll call this set F inverse of X, H prime. So F inverse of H prime is all X and G, such that F of X is in H prime. And I claim F inverse of H prime is a subgroup of G. So I have this set F inverse of H prime. And I want to show this is a subgroup of H prime. So suppose I let X1 and X2 be an F inverse of H prime. What does this mean? Then F of X1 is in H prime, and F of X2 is in H prime. Because this is the set of elements that get mapped into H prime. But F of X1 times F of X2, H prime is a subgroup, it's closed under multiplication, but F's a homomorphism. This is F of X1, X2. This is an H prime, which means X1, X2 is in F inverse of H prime. So if I take two different elements, X1 and X2 and F inverse of H prime, the product is in F inverse of H prime. So F inverse of H prime is closed under multiplication. What about inverses? If X1 is in F inverse of H prime, that means F of X1 is in H prime, which means F of X1 inverse is in H prime because H prime is a subgroup. But the inverse of F of X1 is F of X1 inverse. So F of X1 inverse is in H prime means X1 inverse is an F inverse of H prime. So F inverse of H prime is closed under taking inverses. So F inverse of H prime is a subgroup of H. So if I take any H prime, a subgroup of G prime, its inverse image under F is a subgroup of G. And finally, every subgroup contains the identity. So E prime is an H prime, which means the kernel, which is F inverse of E prime, it's all x and g such that f of x is the identity, is contained in f inverse of h prime. Everything in the kernel gets mapped to the identity, so everything in the kernel is in f inverse of h prime. Now, so let me just redraw this picture. So suppose I have f from g to g prime, a group homomorphism, and let's say it's surjective or onto. So I have the following picture again. I have g goes to g prime. If I have a subgroup h prime of g, f inverse of h prime is a subgroup of g that contains the kernel. And h prime onto means that if I take f, restrict it to f inverse of h prime, this is a homomorphism from f inverse of h prime into h prime, and this is also onto, because every element of h prime has an inverse image in G. So let's recall L of G comma K is all subgroups H such that K is contained in H is contained in G. L of G prime is just the set of all subgroups H prime contained in G prime. So from L of GK to L of G prime, if I take the homomorphism F, it sends every subgroup of G that contains K to a subgroup of G prime. And F inverse takes every subgroup of G prime to a subgroup of G that contains K. And I claim that these functions, this is a one-to-one correspondence, or one-to-one and onto. This function is one-to-one, and it maps onto every subgroup here. So why is all that true? If I take a subgroup H, it goes to a subgroup F of H. If I take a subgroup H prime, it's pulled back to a subgroup F inverse of H prime. And I claim this is a one-to-one correspondence. Why is that? So let's see. Let's draw a picture. G, suppose I have two different subgroups, H1 and H2, both containing K. Suppose F of H1 equals F of H2. I want to show H1 equals H2. If X is an element in H1 and X is not in H2, then we know that Y is an f of H1, which equals f of H2. Sorry. If X is in H1 and not in H2, let's say that f of X1, I'll call that Y1, is an element of f of H1, which is equal to f of H2, implies there exists X2 in H2 such that f of X1 equals f of X2, which means f of X1 inverse X2 is the identity, which means X1 inverse X2 is in the kernel, which means X2 is in X1 times the kernel, which is contained in H1, because the kernel is in H1 and X1 is in H1, and H1 is closed under multiplication. So X1K is in H1, and that's a contradiction. Let me say that again, because I want to try and make sure this is as clear as I can make it. So here we have G, and here we have two subgroups, H1 and H2, and they both contain the kernel K. And here we have G prime and a homomorphism F to G prime. And we have the image of H1, and we have the image of H2. And in fact, suppose f of H1 equals f of H2. These are equal. I want to show the subgroup H1 equals the subgroup H2. So let X1, or let X1, be in H1. So f of X1 is in f of H1, which equals f of H2. So there exists X2 in H2 with f of X2 equal to f of X1. Which means X2 inverse X1 is in the kernel, which is contained in H2. So X1 is in X2 times H2, which is equal to H2 because X2 is in H2. So X1 is in H2. So if X1 is in H1, X1 is in H2. So therefore, H1 is contained in H2. And by the same argument, just interchanging the ones and twos, H2 is contained in H1. So H1 equals H2. So this map from these subgroups to these subgroups is 1-to-1. And it's onto. Because if I take a subgroup H prime contained in G, H equal F inverse of H prime is a subgroup of G, and F of H equal F of F inverse of H prime is H prime, because F is onto. For any element in H prime, there's some element X in H that gets mapped to that element X prime. So if I have the subgroups of G that contain K and the subgroups of G prime, the function F that takes a subgroup here to a subgroup here is a bijection. It's one-to-one and onto. In fact, this bijection has many other nice properties. If we have G, H2, H1, K, and G prime, then F of H2 contains F of H1. So H1 contained in H2 implies F of H1 contained in F of H2. And if I have two subgroups here, H2 prime and H1 prime, H1 prime contained in H2 prime implies F inverse of H1 prime is contained in F inverse of H2 prime. So there's a kind of ordering of subgroups by inclusion, and that's preserved by this function F. And it also proves, I can also show normality. So suppose I have G, N, and K, and a normal subgroup of G. I claim F of N is a normal subgroup of G prime. So the proof has to be easy. Suppose I let X prime be in F of N, or no, or let F be in F of N and Y be in G prime. I better call these primes, because F is onto. This means that X prime equals F of X for X in N, and Y prime equals F of Y for Y in the group G. So if I take Y prime inverse X prime Y prime, that's F of Y inverse F of X, F of Y. This is F of Y inverse XY, but X in N implies Y inverse X, Y is in N, because N is normal. So this is an F of N. So F of N is normal. So I take any element in F of N and I conjugate it by any element in G prime, I get another element in F of N. And for completeness, my own satisfaction mathematically, let me prove similarly that if I have G prime, N prime, the normal subgroup of G prime, and I pull it back, I look at F inverse of n prime, call that n, which contains the kernel. I claim that n, which is F inverse of n prime, is a normal subgroup of G. So that X be in N and Y be in G. So F of X is in N. Of course, N is the inverse image of N prime. So F of X is in N prime. And F of Y is in G prime. N prime normal implies that if I take F of Y inverse F of X, F of Y, that still is an N prime. But this is F of Y inverse XY, which means Y inverse XY is an F inverse of N prime, which is N. Implies N is a normal subgroup. Again, this is all in the notes in the chapter on group theory, and this is what we're doing. So there's a lot of homework problems and a lot of problems in the notes that are not assigned as homework. And the more you can do, the better you will understand all this. Let's see, I have an office hour. I haven't posted it yet. I'll do it right away. Tonight at 7, and also office hours Tuesday, Wednesday, and Thursday. And then we're on spring break starting Friday and all of next week. So we have one more lecture on Wednesday, and then there's week and a half spring break. Not too many lectures left. This is lecture 20. So lecture 21 is on Wednesday. There's one more exam coming up, which means 2 days, a review and exam day. And I'm going to spend a little bit of time after the break talking about ring theory. We've been studying groups, but there also are things in algebra called rings and fields that are important. And that will be the last subject we discuss. Okay. Any questions before we quit for the morning? No. Okay, all. See you on Wednesday. I'll post this lecture right away. Bye, all.